In this chapter, we'll be investigating methods of solving systems of equations and systems of inequalities. A system of equations is like this. This is a system of two equations and two unknowns. And the concept for solution is to find a value for x and y that will cause both equations to be true at the same time. There may be more than one value that is xy pair that causes that to happen. There may be no values of x and y that can cause that to happen. But the idea is that we're looking for values of x and y that will cause both equations to be true at the same time. Now we're going to investigate a number of different methods for solving systems of equations, and then followed by systems of inequalities. Each of the methods will have some advantage over the others in certain situations. So that's why a number of methods are necessary here. The first method we'll look at is a method of substitution, and in that method the fundamental concept is to take one equation, either one, and solve for either letter. And then we'll put that information into the other equation. Here's what I'm talking about. Now, solve one of the equations for one letter. We'll call this equation 1 and this equation 2. Now, it's pretty easy to solve for x in equation 1. It's pretty easy to solve for y in equation 1. It's pretty easy to solve for x in equation 2. And it's a little harder to solve for y in equation 2. So we have a lot of nice options here. If we elect to solve for x in equation 1, all we'll do is add y on both sides. So we find x to be y minus 5. Now, we take this information and we put it into equation 2. So if x has this value, then in equation 2 we can replace that x with that expression. You see, that's what we're doing. So in equation 2, instead of writing x, I'll write y minus 5, and then plus 2y equals 4. You see, I've replaced this x with that expression, and now I have one equation in one unknown. Now, then let me restate that. It's important to realize conceptually what we're doing here, that in this method of substitution, we start with two equations and two unknowns, but by using this technique of substitution, we are reducing the system to one equation in one unknown. Now we can solve that equation for that unknown and then work with that part of the solution. I'll get to that in a minute. All right, let's solve this rascal. We're collecting the y's. We have 3y minus 5 then equals 4. Add 5 on both sides. We find 3y to be 9. Divide on both sides by 3. We find y to be 3. Okay, so y is 3. Now that doesn't tell us the whole story though, because we need an xy pair here. So we take this information about y, that is y equals 3, and we plug it into either of those two equations. So we want y equals 3. All right, now we can use either of the two equations. I'll use equation 1. It looks kind of simple. And actually, you know, I could use this version of equation 1. Because I have solved it for x, I can then use x equals y minus 5. And it's really easy to plug into, you see, in this form. So we have 3 minus 5, so x equals negative 2. Now, that means that the ordered pair, negative 2, 3, should solve the system of equations. Well, let's see if it does. If it does, then it makes the two equations true. If x is negative 2 and y is 3, negative 2 minus 3 is negative 5. Negative 5 equals negative 5. Yes, that one's true. If x is negative 2 and y is 3, let's see, 2 times 3 would be 6. We'd have 6 here, negative 2 here. 6 minus 2, that's 4. 4 equals 4. Yes, truth. So we seem to have a solution to the system of equations. We can check the situation graphically. Now, and we could even solve the system graphically if we want to. Let's just check it for the time being. Now, in checking it, understand what we're trying to do. We're trying to find that point that is on both of the graphs. You see, solving a system of equations graphically works well with our idea that the relationship between graphs and equations, and it comes up again and again, doesn't it? That every graph has points on it, every point has coordinates associated with it, and the coordinates will solve the equation. Well, if we want coordinates that solve both equations at the same time, then we need the intersection point of the two graphs. That's all there is to it. Okay, let's do that. Now, to put these equations onto the graphing calculator, though, we need to solve them for y. So let's slide over here. Equation 1 To solve for y, we would subtract x on both sides and then multiply through by -1. And this is the expression we'll put in for y1. And then for the other one, let's see, we'll subtract x on both sides and then divide on both sides by 2 to find y equals this fraction. Let's see what it looks like. When entering the fraction for that second equation, notice that I'm containing the entire numerator within parentheses. It would mean something different if I didn't put the parenthesis in. Well, using standard settings, now I'm pressing number 6 here, the graph looks like this, and I would like to have more friendly settings in order to trace to that point of intersection, especially if I think it's going to be an integer value. So I'll press zoom and press decimal number 4, and here's what the graph looks like. Now, often the trick here in using the graphing calculator is getting a nice view of our intersection point. Now, we're almost off the graph here, and we could actually trace to this point as we are. We could press the trace button, but I would like to show you how to get a nice frame on that intersection point. Let's press window, and I need to try to move my view to the left a little bit and up a little bit. Now, for x minimum and maximum, you know that the friendly setting is one that gives us a total horizontal distance here of 9.4. So the total here is 9.4. If I want to change and sort of move my thinking to the left, I can simply do this. I can move this to, let's say, -0.07, and then the x max would be, well, let's see, what do I need on the other side to give 9.4? Well, I'd need 2.4. Okay, and now I'd like to move it up a little bit. I'm noticing that the total vertical distance, I'm just adding 3.1 on one side of the x-axis and 3.1 on the other side. That's 6.2. And I just have to maintain the idea that I want to keep a total of 6.2. So I'll go -1 for the minimum, and then the max, I'll go 5.2. And this will give me both a square perspective and some friendly settings when I press trace. All right, tracing. Now notice I'm on the bottom graph. I'm going to go to the left a little bit and show you what happens here when I press the down or up arrow key. I go to the other graph, and the equation for the graph is listed in the upper left-hand corner. Here I'm on equation number 1, and when I press the up or down arrow key, here I'm on equation number 2. Well, let's go over to the right to an approximate intersection point. It looks like, well, it looks like it's right here. But I can verify it for sure by just pressing the up or down arrow key and jumping to the other equation and noticing that the y component doesn't change. And that's an important idea in identifying a point of intersection. You want that y component not to change when you jump to the other graph. Notice in this system of equations, our top equation contains a third-degree polynomial, and we know that that translates into a curvy graph, as we'll see in just a little bit. Let's use the method of substitution and solve the system algebraically. Now, to solve algebraically, we know that by substitution, we want to solve for one letter in one of these equations and then plug that information into the other equation. Looks like to me that the first equation is already solved for y, because y is isolated here on one side of that equation. So if we call this equation 1 and this equation 2, then we can take this information about y and put it into equation 2. So we're just going to rewrite equation 2 and replace this y with that expression. All right, let's go. We've got 2x then, and instead of y, I'm writing the expression x cubed minus 3x squared plus 3, and then now back down here equals 3. All right, now I want to solve this. Notice though that conceptually we have taken our two equations and two unknowns, and by substituting we have reduced it to one equation and one unknown. And now we use the techniques that we've learned in the past to solve this equation. Well, we would write this in sort of a standard form and attempt to factor. Let's do that. The term of highest degree is x cubed, and then we have minus 3x squared. And we have this x term. And I'm noticing that if I subtract 3 on both sides, that both of these constants go out. So I have equals 0 here. Now I'd like to solve by factoring. I can snag out a common factor of x, and I'm left with x squared minus 3x plus 2. And then I'd like to factor the quadratic factor. Turns out that it factors rather easily. X times x for x squared, both signs are minus. Factors of 2 are just the 2-1 combination. And the zeros for these factors are x equals 0, x equals 2, and x equals 1. So these are the x coordinates then for the solutions to the system of equations. Now what we need to do is take this information about these values of x, though, and pop that information into either of these original equations. It looks like to me it would be easier to plug into equation 2 than it would be into equation 1, so let's do that. If x is 0, here's what we're doing. We're just taking equation 2 and replacing x with this value and evaluating for y. The term goes out, y is 3. So the ordered pair 0, 3 should be on both graphs and therefore should be an intersection point. Now when x is 2, replace the x with 2 and evaluate. This becomes 4. Subtracting 4 on both sides, we find y to be negative 1. When x is 2, y is negative 1, so the ordered pair 2, negative 1 should be an intersection point of the two graphs and should be a solution to the system. When x is 1, replace x with 1 and evaluate for y. This term becomes 2. Subtract 2 on both sides. We find y to be 1. So when x is 1, y is 1. So the ordered pair 1, 1 should be an intersection point of the graphs and should solve the equations as well. Well, let's see. Let's check this graphically using the calculator. The equations have been entered, and I'm going to use standard settings here. I'm either pressing number 6 or cursoring down and pressing enter. And I'm noticing how the graph behaves at this setting. But really, I need friendly settings to be able to use the trace button to identify those points of intersection. And all 3 of those points of intersection are in this region of my coordinate plane. So let's see how the view changes. Whoops. As I press zoom and then z decimal number 4. I get a much closer view. And this view is adequate to identify those points of intersection. Press trace. Now it appears that I'm already at one of those points of intersection. One of the ones that we said, one of the solutions for this system was at 0, 3. Now we can verify this as a solution by jumping to the other equation by pressing down or up arrow and noticing that y doesn't change as I go from one equation to the next. Whereas if I'm not at a solution point, like at a point like this, and I press up or down arrow and jump to the other equation, the y component does change. All right, let's go to the other solution points here. I'm supposed to have one in this, let's see, this neighborhood at 1, 1, and I can verify that as a solution point. There we go. And then going over to the other spot that looks like an intersection point, I'll verify that as a solution point. 2, negative 1, sure enough. In the last couple of problems, we've used graphing just to check the solutions that we have found algebraically, but it turns out that graphing can be used to actually solve systems of equations. And sometimes the graphical method is much easier than the algebraic method. For example, consider this system of 2 equations and 2 unknowns. Now notice, y is e to the x for our first equation, and our second equation looks pretty normal. But if we take the information in equation 1 and put it into equation 2, look at what we have. Now it's already solved for y, so in place of y right here, I'm just going to write e to the x. So we would have x minus e to the x plus 1 equals 0. Now we have a variable in both an exponent and we have a variable that's a term in the equation. You might work with this a little bit and see if you can manipulate it to a point where you can isolate x or solve for x here. But it's a really tough problem using that method. But it's really easy using the graphing method. Let's have a look. The 2 equations are already on board, and the graphs corresponding to those equations, well, here they are. Pressing trace to identify that a common point on the 2 graphs, well, it looks like we're already on it. If I press the down arrow key, I'm jumping from equation to equation or from graph to graph, and I'm noticing that the y component doesn't change. So x equals 0, y equals 1 is a solution to this system. Now let's verify 0, 1 as a solution to the system algebraically. We found x to be 0 and y to be 1 as our solutions. In equation 1, replacing x with 0 and y with 1. Let's see, e to the 0 power would be 1, so we get a true statement. So that ordered pair solves one of the equations. For the other equation, replace x with 0 and y with 1. These go out, and so we have 0 equals 0, and our solution is verified. Suppose you are setting up a small business and have invested $16,000 to produce an item that will sell for $5.95. If each unit can be produced for $3.45, how many units must you sell to break even? I've outlined the important information in the problem right here. We have $16,000 invested. The selling price is $5.95 per unit. The cost is $3.45 per unit. Now we want to set up a couple of equations that relate all of this information. Now the total expenses involved would be the $16,000 setup cost, or the investment, plus $3.45 for every item that we sell. Now let's let x stand for the number of items that are to be sold. So it's $3.45 times x to give the cost per item, the cost of the items that are sold. Now the revenue, the income, is calculated as the income per unit, the selling price per unit, times the number of units sold. Now, conceptually, it should make some sense that if we're looking for a break-even point, then we want the point where the revenue is equal to the total expenses. That means, with using equations, it means that the revenue is equal to the expression for the total expenses. And now we solve this equation, and we find x to be 6,400 units. The point of showing this problem is that we simply organize our information, and we're setting up equations involving unknown quantities. And a lot of times in setting up these models, we're using words and word phrases. And we've done this kind of thing before in the past. But now we're looking to set up two equations in two unknowns, because that's the kind of chapter that we're involved with. Now just understand, too, that there are other ways to solve these problems. I mean, this problem has a rather simple arithmetic form that we could take for solution. I'll show it to you here right quick, just so you'll know what I'm talking about. But if the income is $5.95 per unit and the cost is $3.45 per unit, then on a per unit basis, we have a profit of $2.50. So if we can make $2.50 on every unit, in order for us to find out the break-even point, we can just divide $2.50 into 16,000, the amount of the investment, you see, and discover the number of units that have to be sold. So although there is an arithmetic way to deal with the problem, we're in a chapter where we're setting up systems of equations. So that's the approach that we want to use in order to get practice, in order to solve more complicated problems later. Let's look at this one. A total of $18,000 is invested in two funds paying 7.75% and 8.25% simple interest. If the yearly interest income is $1,455, how much of the $18,000 is invested at each rate? This problem may look vaguely familiar because we've had problems like this in the past, but we've solved them using a somewhat different technique. Now, we can begin the solution to this problem in much the same way that we did before, but let's keep in mind that in this chapter we're looking to set up two equations in two unknowns, and we're not confined to just one equation in one unknown. All right, the basic idea, though, is the same as before. If we have $18,000 invested, and some of that money is invested at one interest rate and the rest of it at another interest rate, and the total amount of interest is given to us, then one basic idea for an equation is that the interest earned at one interest rate plus the interest earned at another interest rate is equal to the total interest earned. And we could go further with that. We could say, well, interest is some principal times rate times time. That's how we calculate interest. So this is just some PRT. And this also is just some PRT, and the total interest is $1,455. Now, to represent the PRT, the principal rate and time, for each interest rate, we can kind of use a different technique than we did before. When we solved these problems in the past, we said, okay, let's let the amount invested at one interest rate be equal to X, and then the amount invested at the other interest rate is Well, let's see. It would be calculated as the total investment minus the x. You see, so we're using one unknown to represent two unknown quantities. And that's the technique that we used in the past. Now we have the luxury of using two unknowns. So we'll just let the amount invested at one interest rate be x and the amount invested at the other interest rate be y. So here I could show it like this. I can say, okay, let's just let x be the amount invested at this interest rate and y be the amount invested at that interest rate. And then it makes making this equation rather easy. That is, the principal associated with a rate of 7.75% is x. So the principal is x, the rate is 7.75%. Now notice I'm expressing it as a decimal here. The time is 1 year, so I've not listed anything here because it won't make a difference in the problem. And for the other one, the principal times rate times time is y times that interest rate and times a t of 1 equals 1455. So this is one of our two equations, and I'll come back and clean it up here in a little bit. But the other equation in problems like this, when they even sound really complicated, if you identify your two unknowns, then and you realize that you're trying to generate two equations involving those two unknowns, many times one of the two equations is relatively trivial. It'll either be the sum of the two unknown quantities or the difference or maybe the product or there'll be some simple relationship involving the unknown quantities. Here, that simple relationship is that if x is some amount of money invested at an interest rate and y is some amount invested at the other interest rate, the total of x and y is $18,000. You see, this is the total investment. So one equation is just x plus y equals 18,000. And our other equation is given down here. Now, we're going to solve the system in just a second, but I want to show you another technique here. In addition to setting up the two equations, I want to show you a technique for cleaning up rather complicated looking things like this. We know from previous work that we can clear this decimal by multiplying through by 10 or 100, 1,000 or something like that. That will slide the decimal point over an appropriate number of places. Now here we would want to slide over 1, 2, 3, 4 places. So we need to multiply by 10,000. So when we do that throughout this equation, this becomes 775x. And this term becomes 825y. And then this one, we have to tack on 4 zeros to the end of these digits, and we get a pretty big number. Now, when you have big numbers like this for coefficients and a constant, look out for the possibility of dividing through by some kind of common factor. Now, here I found that we could easily divide through by 25. So I divided by 25 here, here, and here, and it simplified things quite a bit. So, all right, now that we have our two equations, we go into this kind of form. Now, remember, the first equation, the simple one, was x plus y is 18,000. The other, from the bottom of the board over here, is this. And now we're looking to solve this system of equations using the method of substitution. So we would look to solve one equation for one letter. It's really easy to solve in equation 1 for x, let's say. So solving for x, we find x to be 18,000 minus y. And then we put this information into equation 2. So in place of this x, we're going to write that expression, 18,000 minus y. Pop it in, and away we go. And I'm confident at this point that we could solve the equation. Once we solve this equation, we find y to be 12,000. Now, where are we in this problem? We're at a place where we've solved for one of the letters, but we need the value of the other letter. And we find that by going into either of the original equations and putting in this information. It's pretty easy to tell that if y is replaced with 12,000 here, that x will need to be 6,000. So we find x to be 6,000. Now, with word problems particularly, we need to make some kind of interpretation. We need to kind of look back at the original problem to see where our labels were, to see that $6,000 was the amount invested at 7.75% and that y was the amount invested at the other interest rate. So we write our answers kind of like this. And we're pretty much finished. But just use the information that we learned in previous chapters about generally setting up mathematical models, and then look for the two equations involved in the model that you're dealing with. And one of them will usually be a pretty simple equation, and the other will follow the nature of the problems that we've had in the past.